mind. I think first is clear to you. Now let us understand the second point quickly. As soon as the vessel is accelerated, the water surface has the tendency, or it inclines itself perpendicular to net acceleration. Very important point. So suppose this is the accelerated vessel. So first what we will be doing, we will be analyzing in frame of vessel. So we will be just reversing the direction of acceleration to this water column. Let me make this water column. We will be reversing the direction of acceleration, and also the gravity is acting downward. Don't forget it, it is acting downward. So now we are in the frame of vessel, and all the things are now in rest with respect to vessel. So we can now analyze our what was our second point, that along means perpendicular to net acceleration, water inclines itself. So let us now find the net acceleration. What is net acceleration with respect to vessel only? Here one acceleration is along negative x direction, and one acceleration, which is acceleration due to gravity, is along negative y direction. So net acceleration by vector law of addition, it will be a square plus g square. Okay, or you can write in vector form like this. In a x direction, acceleration is minus a, and in y direction, acceleration is minus g. So a net in vector form is ax plus ay, which is minus a I cap, okay, in the negative direction, and this is minus g j cap. Okay, I hope you have a thorough idea of vectors as well. So net acceleration magnitude, if we want to find it, will be a square plus g square. So I wrote it directly here. So now this net acceleration is actually perpendicular to this surface. It will be perpendicular to this surface, and always the water will inclines itself perpendicular to the net acceleration. If net acceleration is this, then water must inclines itself like this, perpendicular to net acceleration. So it's inclined like this only. So I hope this point is also clear to you. Now let's take the third point. So what does third point says? When vessel was at rest, uniform and same pressure acts on bottom surface, but in accelerated vessel, this is not the case. The pressure effect on bottom decreases from place of more water to the place of less water. So let us understand this point as well. So to understand third point, here we are with our diagram. So consider 2 points. This is point 1 and point 2. We will also be making the condition when there was no acceleration. No acceleration exists. So water surface was at rest. It was not moving, and at that time we will be taking these corner points again, 1 and 2. Now from this water surface, the height will remains the same. It will be h, because this is plane here. But now this point 1, from the water surface, it will have a height of suppose h1, and this point 2 will have a different height from this surface of water, that is h2. And if we will consider any intermediate point, suppose this is another point, third point, it from surface of water, it will be having a different height again. This is another different height. So all heights are actually different here, but all heights were same here. So because of this, the pressure at this bottom plane was actually, suppose the atmospheric pressure is existing here. So if we have to find the pressure at this point, so by Pascal's law we can easily find it. The pressure will be P0 plus rho gh, and it is uniform throughout this plane. But here what's the problem, that at this point P1, the will be written like this. The pressure here is P naught, means at all these points the atmospheric pressure acts. Okay. So since this point 1 is away from the surface of water or the atmospheric pressure, a height of h1, so pressure at this point 1 will be P naught plus rho g h1. Similarly, at this third point, P3 will be P naught plus rho g H3. At this point, the pressure will be P2, P naught plus rho g H2. Clearly, P1 is greater than P2. Pressure at this point is greater than P2, and P3 is greater than P2, but P3 is actually less than P1. So maximum pressure acts at this point, at this corner point, the first point where more water exists. Here more water is there, so more pressure is actually acting at this point. And how I have written this P1 is greater than P2, because this P naught is constant in this both, P naught plus rho g h1 and P naught plus rho g h2. So P naught is actually constant in both of this, but h1 is greater than h2, because of which the P1 is greater than P2. Since h1 is greater than h2, therefore the pressure 1 is greater than pressure 2. So very important concept, and a bit shocking, because earlier uniform pressure was acting here, but now different pressure is actually acting at the bottom.